Hi there, in this lesson we're going to look at graphs. This is our next data structure that we're going to cover, and you've actually already seen sort of a picture representation of this when we were learning about trees, where we had nodes and then those nodes can have two children, binary trees. You've seen that with the binary search tree as well as the heap, and this is somewhat similar in terms of how to think about the way the data is. It's in these things called nodes, and then you have these links between the nodes, but this is actually a new data structure representation of that idea, and this is referred to as graph. This is a graph data structure, and there are some differences in the terminology as well. In the graph world, these nodes are referred to as vertices. Okay, so this graph right here can be represented by its vertices. So I could do V, and inside of these curly braces I can say, okay, A, B, and C. These are the vertices of this graph, and the edges, right, the blue lines here, these are the edges that connect one vertex to another. This can be represented like this. I can have E, and in these curly brackets I'll basically write down what the edges are, and the way edges are represented is from the vertex to another vertex. So between A and B, this is one edge, all right? And then between B and C, that's another edge. So let me write that down. And then finally, we have another edge between from C to A. And that's going to be right here. I'll put that on the next line. Okay, so these together represent these edges. Now, since there's no direction, right? There's no direction between A, B, B, C. We can think of these as BA and CB. And AC, the other way around as well, okay? So that's an important point to keep in mind. This graph, let me change the color here. This graph is known as an undirectional graph, all right? And contrary to that, on the right, this is a directional graph for obvious reasons. You can see the arrows, right? From to get to vertex B from A, we have to go in this direction. That's basically what this is saying. We can't go in the opposite direction from B to A. The arrow is saying we can travel in this direction, okay? So this is an important distinction you want to keep in mind. There are two types of graphs. We have undirectional graphs, which is right here, where you don't see any arrows, and then there are these directional graphs, all right? And the second one is a directional graph. And any graph can be represented in this fancy notation, which is honestly pretty simple. You put a G, and then it's represented by its vertices and edges. All right, that's it. This is what represents in math. This represents a graph. G is equal to the set of vertices and the set of edges. Just some mathematical notation, which honestly is not really important. I just wanted to show it to you in case you ever come across it in an interview or something like that. So let's come over to the directional graph. Now, to represent the vertices for this directional graph, I could do it's going to be A, B, C, and D. These are the vertices for the directional graph. And the edges are going to be A to B, right? And that order is important. This order is important from A to B. I can't have it B to A. A, comma, B means A comes first and then you travel to B. And then from B to C, that's another set, right? So another edge, B and then C. And then we go from C to D. And then we go from A to D. And then finally we have from C to A. All right, so these are all the edges. These are all the edges of this directional graph. Now, just a little bit more terminology. There's a word called path. And as you might guess, a path is basically the vertices that you visit on your way to get to a final destination. All right. So let's say if I need to get to D from C, the path to that will, of course, be C, A, and then finally the destination D. All right. As a matter of fact, I can go from C to D directly. There's an arrow pointing from C to D, so that's another path. And there's another term called degree. The degree is the number of edges that are connected to a given vertex. Okay, so for example, A has 2 degrees, and B has 2 degrees, and C has also 2 degrees. If you look at A, we have 2 outgoing degrees, right? Where this is one of the outgoing degrees, and this is the other outgoing degree, and then we have 1 incoming degree. So the concept of degree is exactly the same, but it's just we have to term it as incoming degree and outgoing degree. So there are 3 degrees, 2 of which are outgoing and 1 of which is incoming for the vertex A. For vertex B, we have 1 incoming degree and 1 outgoing degree. And for vertex C, we have 1 incoming degree and 2 outgoing degrees. All right. And D just has 2 incoming degrees. Simply put, a degree is basically the number of edges that are connected to a particular vertex. And in the case of a directional graph, we also term it with the direction, whether it's incoming or outgoing. Now you might be wondering, what are these sorts of data structures used for? Well, there are a variety of problems that these data structures can solve. For example, let's think about Facebook friends. You may have a friend who is a friend of someone else who is a friend of someone else who may also be your friend. And this sort of a circular relationship of friends could be mapped out in a graph. So let me show you that as an example. Let me wipe the screen here. Let's say that Paul is friends with Robert, and Robert is friends with Casey. And further, Casey might be friends with someone named Michelle. And Michelle may have a friend named Bill. And not only that, Paul might be friends with, let's say Michelle is friends with Robert, and she is also friends with Paul. So this is an example of an unidirectional graph, because if Paul is friends with Robert, then of course Robert is also a friend of Paul, isn't he? So both of the relationships exist. And an unidirectional graph, in reality, behind the scenes, what it is it's a 2-directional relationship. This is exactly the way you want to think about it. It's a 2-directional relationship. An unidirectional graph is a 2-directional relationship. All right. So let me just wipe those clean. That's how I want you to think about it. Casey is not directly friends with Paul. All right. And Paul is not directly friends with Bill. Robert is not friends with Bill. Casey is not friends with Bill. But Bill is Michelle's friend, and Michelle is Bill's friend. Poor Bill, according to this graph, only has 1 friend. This graph is, of course, incomplete. Bill may have other friends, but Facebook has massive graph data structures like this with a very, very complex network of relationships, and they manage it using graphs. Now, these Facebook friends relationships are unidirectional. Let me give you a real-world example of a directional relationship. Let's say that, similar to the one we have up here, instead of drawing a new one, I'll just use this as an example. Let's say that these are one-way streets, okay, one-way streets, and these are homes that are at the end of the intersection, okay? So you cannot go in the opposite direction. You may wind up getting a ticket, or worse, you might even get involved in a car accident. So, of course, that's an example of a directional relationship. To get to home B, we can't go directly from C. We have to go to A and then from A to B. That's just how the one-way street rules might be set up. So that's a real-world example of a directional graph. Another example that I can think of is Webpages. When you visit a particular website and you click on a link, that may take you to another page, and then you click on some other link, that may take you to some other page. But that doesn't mean that you can go back by clicking the links, all right? There may not be another link to take you back to the original location, right? So that's a directional relationship between your origin and your destination as you browse around on the internet. Now, you might be wondering, how is this data structure managed in a computer program? When we look at these pictures and we see these vertices A, B, C, and they're connected with these edges, the picture looks pretty straightforward, right? We can understand the relationship between these vertices. But in a computer program, how do we manage these relationships? There's a term that I want to introduce you. It's called adjacency. And it is exactly what it sounds like. Something that's adjacent to something else means it's a neighbor or it's next to it. So for example, A, this vertex is next to B, right? So it's adjacent to B. And A is also adjacent to C, right? Same thing goes with C is adjacent to A, and C is also adjacent to B. And same goes with this vertex B. And when you come over to this directional graph, the same thing applies. A is adjacent to B as well as to D. So this concept of adjacency basically means neighboring, right? Something that's next to something else. So we need to represent this adjacency in a computer program using one of two ways. One way is to use a multi-dimensional array where we have the first set of brackets representing the rows and the second set of brackets representing the columns. And the output is basically something like this matrix. And this actually is called an adjacency matrix. Notice how at the intersection of row A with column B, there's a true value there. At the intersection of AC, there's another true value, right? So these intersections represent the edges, okay? They represent the relationship. If we move to the next row, B is adjacent to A, isn't it? So there's the link. That's why there's a true value here. B is not directly connected with B itself, right? There's no self loop, which is not important to think about right now, but basically B is connected with C, and then C is connected with A, and C is connected with B. So if you look at this matrix, notice that it's symmetrical. This L right here is exactly the same on the other side. So if you could just cut this right down the middle diagonally, the structure is the same on both sides. That's always going to be the case with a non-directional graph. Contrary to the non-directional graph, take a look at the directional graph's adjacency matrix. This is not symmetrical. And the way that you want to read this is start from A, and you see that A is, the row A has an intersection with column B, right? So that means A is adjacent to B, and A is adjacent to D. And same thing goes for the next row. B is adjacent to just C. And C is adjacent to A as well as with D. And D, the last column, is, we're not representing the relationship here because there's no outgoing adjacency. We just have incomings. So you want to think of this row by row. Now what we're going to be using is, instead of using a multi-dimensional array, we're going to be using something called an adjacency list, okay? This right here is referred to as an adjacency matrix, but we're going to be using something called an adjacency list. So let me show you exactly what that looks like. So for the adjacency list, I'm going to use another example. Think of these as the vertices, and we're going to start forming edges between them, and then I'll show you exactly how we can convert these relationships between these vertices into an adjacency list rather than a matrix. So let's say that for the 0 vertex, it points to 1, 3, and 2, right? This is a directed graph, right? There is direction here. So 0 is adjacent to 1, 0 is adjacent to 3, and 0 is adjacent to 2. Now, can you take a guess as to how this would be represented using an adjacency list? We can have an array, and in each slot of the array, we can have lists. So for example, in the 0th slot of the array, we can have a list containing the elements 1, 2, and 3. And you've already looked at lists. We covered singly, doubly, and circular linked lists earlier on. Well, I'm going to show you an example where you can use a built-in Java data type called an Arraylist, which is very similar, but it basically is an extension to the array data structure. But think of it as a list. So in the 0th index position of the array, think of this as the array. At the 0th index position of the array, we have this list containing the numbers 1, 2, and 3. All right, and let's say there's another relationship between 1 and 2, and then 1 and 4. So 1 is adjacent to 2, and 1 is also adjacent to 4. So at the 1 index position of the array, we'd have a list containing 2 elements, the number 2 as well as 4. All right, and then the next relationship here, 2 is also adjacent to 3, right? In this direction, this is a directional graph, so direction is very important. So at the second slot of the array, well, not second, but the third slot of the array, which is index position 2, it has just one number in the list. Okay, this is still a list. This is still a list inside of the index position of 2. And in that list, we only have a single number, which is 3. Now, let's say 3 has an adjacency with 1. So then in the 3 index position of the array, we'd have a list containing just one element, which is 1. And let's take an example with 4. 4 is adjacent to 0, and 4 is also adjacent to 3. So in the fifth slot of the array, with index position 4, it'll have elements 0 and 3 in its list. Okay, so the idea is we have an array of 5 slots, and if we count these vertices, 1, 2, 3, 4, 5 vertices. Okay, so we have 5 slots. Again, index position of an array starts from 0 all the way up to the length of the array minus 1, which is 4. So in each one of these slots, we're representing the adjacencies. Okay, so again, at the 0th index position, the number 0 here, this vertex, is adjacent to 1, 2, as well as 3. You can follow the arrows right there. And then at the 1 index position of the array, it's adjacent to 2 and 4, and so on. Hopefully you get the idea. So let me show you in Java how this is going to work. So here I have the package ds.graph. You should already have this code. And open it up and navigate to the app class. So in this app class, I have the main method, and here I just want to show you how we can use this data structure that I'm about to go over. This is the graph data structure, and the class for that exists right here, which we'll see in a second. So I'm initializing a graph structure with 5 slots, right? 5 vertices, that's what this means. And we're going to add the edges, okay? That's what this add edge method, it exists in the graph class, and we're going to cover that shortly. So to add an edge between 0 and 1, 0 and 2, 0 and 3, we do exactly as it's showing right here. And then to add an edge between 1 and 2 and 1 and 4, we basically do this. So after we fill the graph here, the next thing is we can use this adjacent method, which I'll show you. This ADJ basically means give me the data that's adjacent to this vertex. So to the 4th vertex, right, the vertex containing the number 4, what is adjacent to it? Well, let's hit run and notice that it's going to print the values that are adjacent to 4, and that's the number 0 and 3. And if you go back to the way we inserted this information, notice that the vertex 4 has 0 as the adjacent number, as well as the number 3 that's also adjacent to 4. All right. Now if I change this to, for example, let's see another vertex here. Let's try the number 1. Right. Now let's hit run, and it's going to show me the number 2 as well as 4, as it's showing right here. Right. So this is just a method that I implemented on the graph class, and it's showing me all of the adjacencies for the given index. Okay, or the vertex, the given vertex in this case. So let's go into the graph class, and I'll show you how I implemented it. So these are 2 member variables of this class, vCount and eCount, which represents the number of vertices and the number of edges. Now I have this object called an Arraylist, and it's a built-in Java data type. And typically, the way this is used in Java 6 onwards, is we have to put the data type that this particular object accepts, right? And we can have this generic implementation where it's saying, okay, make sure that any data that goes in here, it must be of type integer. All right. Now, since I didn't cover this throughout the course, I'm not going to leave that in the code. We have an adjacent variable, which is going to be an array of integer lists. Okay, so each slot of the array is going to contain an array list. And to initialize this graph, the way we're doing it here in the app, we're initializing the graph by giving it the number of vertices that are in our graph. We give it 5 vertices. So what's going to happen is it's going to take that count. It's going to set the vCount, right? The number of vertices. This variable is going to be set to the initialization. And right here, the eCount is 0 because once we start, we just give this 5 here. we just give the number of vertices. We don't actually mention the number of edges yet. So we just give the vertices, so eCount is set to 0. And then finally we initialize the array, and it's supposed to be initialized with the number of vertices, right? So we create an array of the number of slots equal to the number of vertices, right? And each one of these slots is going to contain an array list. So now we can just basically loop through the number of vertices from 0 to the number of vertices. And for each one of the slots of the array, we're inserting a list, an empty list containing no data. And here's a generic version. We're adding this integer here. I'm going to remove that for this code because we haven't covered generics. But understand that if you come across code with that, angle brackets, that's a feature of Java that allows for type safety. And that just ensures that the ArrayList object only gets integer data. In the spirit of not introducing much syntax, I just want to get the general idea across. We're going to be using this ArrayList without the integer generic. At every slot of the index, we are basically throwing in an empty list, all right? And then down here, this is just a method that's going to return the number of vertices if we ever need to. And this is a method that's going to give us the number of edges, right? It returns eCount. So obviously, eCount right now is 0. When we start to add edges, when we start to add the relationships between one vertex and another, the source and the destination, that's when the eCount is going to be incremented. And how do we add an edge? Well, we just, we invoke this method called addEdge, and we give the source as well as the destination. And that's going to basically, at this index position of source, we're going to add, right? We're going to add the destination, all right? And this is essentially adding to the list. So each one of these slots contains a list. So we're adding to that list the value that is the destination, all right? And then finally, this is the method that is, that's going to show us what are adjacents to a given vertex, all right? And all this does is goes to the particular slot position of the array and just does a toArray method, and this just returns an array, and it's going to return an array of objects. But this is the abstract data type, right? This is the general idea of a graph data structure. And the way we manage these relationships between a vertex and another vertex, we can use an adjacency list implementation like I showed you here. Another thing I want to show you is that we can use a linked list. Instead of an array list here, we can have, for example, the singly linked list data structure that we covered earlier. So remember this singly linked list structure? We covered it several lessons ago. You can actually use this singly linked list data structure to be the one that sits in every single slot of the array, all right? And that's going to work exactly the same way. So you can try that, play around with this, try to implement your own graph data structure using this singly linked list. All right, it's that time again. It's time for a pop quiz, or not really a quiz, but it's actually an assignment that I want you to work on. And that's going to be to enhance this graph data structure. Notice the limitations this data structure has right now. All right, the way we implemented it, this requires the vertices to be the same as the slots of the array, right? So if the vertices are, for example, the number 10, 12, 14, and 8, the way we've written this code, those index positions would need to exist in an array, and that array would need to be that big to support those vertices, right? So that's not really a clean implementation. So I've already given you a hint that you can use the doubly, or rather the singly linked list structure to enhance this. So that's the assignment. I actually want you to update this graph data structure to be able to support different kinds of graphs, directional graphs. And the example I want you to keep in mind is, let's say we have a very complex bus route, going through different streets. We have State Street, Avenel Street, Elm Street, William, and Pocono Place. These are 5 streets. And notice the arrows. The bus could take a variety of different directions, but these are the directions, okay? So, and you can also think of these as one-ways, moving from one street to another or whatever. But basically, this is the graph. How would you modify the graph data structure to be able to support this representation, right? If I needed to add an edge between, say, State Street and Avenel Street, how would I do that? So this I'm going to leave with you as an assignment to complete. Make sure you work on this, and then you can resume to watch my solution. And there's a variety of ways you can do this, but I'm giving you a hint. You can use the singly linked list data structure, and you don't have to use that particular class that you've written already. You can create your own new representation of a linked list and make it happen for this problem. So give that a try on your own. As a matter of fact, let me give you some structure for this assignment so you know exactly what you have to do. And I've actually ended up pausing the recording, and I completed this class called Better Graph, just so that I can run it in front of you and show you what the output should be like. So I expect you to write your own version of this Better Graph, and more importantly, if we go to the app class, I'm going to show you how we can use this data structure so your code should behave the way I'm showing you here. So whatever you do for Better Graph, it has to support these functions. You need to be able to add the different vertices, right, as I'm doing here, add vertex method. And then you need to also be able to add the edges between these vertices. So the way you want to use this Better Graph is you first initialize it with the number of vertices right here. The first argument is the number of vertices, and then the second argument is whether it's directed or not directed. And in this case, it is directed, as you can see by the diagram here. And after that, you start to add the vertices. All right, so we keep adding the vertex one at a time. We have State, Avenel, Elm, Pocono, and William. 5 vertices here. And after you're done adding the vertices, we want to add these edges between the different vertices. So State to Avenel, State to Elm, Elm to Avenel, and Elm to William, William to State, William to Pocono, and so on. Order doesn't matter, but you want to make sure you get the direction correct. All right. State goes to Avenel, right? Avenel doesn't go to State. State goes to Avenel. State goes to Elm. All right. So direction is important here. So you want to add the edges in that order. And then finally, you can invoke this print method on this data structure, and it'll print the relationship. So just so that you have an idea how this is going to look, if I hit the run button here, notice the output. So what this is saying is that State is adjacent to Elm as well as Avenel. Right? State is linked with Elm, and then State goes to Avenel. Avenel here goes to Pocono. Elm goes to William, and then Elm also goes to Avenel. Pocono goes to Elm, and William goes to both Pocono and State. Okay, so that's what this is showing here, this print method. So I want you to implement that as well for this assignment. Okay, so hopefully this gives you a good overview as to what you need to do to complete this problem. And you're going to be creating a class called Better Graph, which I've already created here. I paused the video and pretty much banged it out. But take your time, try this out on your own, and the end result should be, when we invoke this print, it should print out the relationships as it's showing right here. Okay? And the order in which you add these edges does not matter. So I can take this and put this all the way to the bottom, take this and put it on the top. That does not matter, as long as the direction between these streets, between these vertices, is correct. Avenel is first, and then you go to Pocono, as you can see by the diagram. So try this out, and then in the next lesson, we can go over my solution.